Okay, so let's take a look at section 4.1 and 4.2. So let's look at a theorem here. It's the existence of unique solutions. We're not going to prove this theorem. We're not going to prove this theorem. I'm just going to state it here. So it says the initial value problem a n x. A n x is some function of x times the nth derivative of y plus some function of x, a n minus 1 x times n minus 1 derivative of y all the way down to some function of x times y equals some function g of x with y of x0 being y0, y prime of x0 being y1, dot dot dot, n minus 1 derivative of y of x0 being y n minus 1. So it has a unique solution on an interval I containing x0 if these coefficient functions and the g of x function are continuous on I and they're not equal to 0, these coefficient functions, for all x in our interval I. And moreover, if g of x is 0, then the differential equation is said to be homogeneous. Okay, so this is a big theorem, but we're not going to prove it in this class, but we're going to use the result of this theorem. Okay, so now I'm going to erase this theorem and we're going to look at some more things. So let me do that. Okay, so let's look at proposition 1. So it says if y1x and y2x are both solutions of the homogeneous equation y double prime plus px y prime plus qxy equals 0, then y equal to c1y plus c1y1 plus c2y2 is also a solution for any constants c1 and c2. So this is saying that any linear combination of two solutions is also a solution of this homogeneous equation up here. Okay, so let's take a look at the proof here. Okay, so we're going to assume then that y1 and y2 are solutions of the homogeneous equation up here. And we need to show then that y equal to c1 y1 plus c2 y2 is also a solution. So for y1 and y2 to be solutions, it means when I plug them in up into the differential equation, they should equal 0 on the sides. Let me just note that here. So note here that y1 and y2 solutions implies, so when you put y1 in place of y up here, so y1 double prime plus p of x y1 prime plus q of x y1 equals 0. And also when you put y2 in place of y up here, it should equal 0. So y2 double prime plus p of x y2 prime plus q of x y2 equals 0. Okay, now I want to show that y equal to c1 y1 plus c2 y2 is also a solution. So let's take my equation 1 and multiply it by c1 and take equation 2 multiplied by c2 and add them together. So let's do that. Okay, so doing this calculation, so multiplying equation 1 by c1, so I did it up here on both sides, and multiplying equation 2 by c2, I've done it here and here. So now we're going to add these. So we're going to add this column, add this column, add this column, and add this column. So doing that, we get then, okay, so adding the c1 y1 double prime with the c2 y double prime, we have this. Then it'll be c1 times this guy, c2 times this. I can factor out the p of x, which I've done here. Then it'll be c1 y1 prime and c2 y2 prime. And this guy here, I can factor out the q from these two terms over here. It'll be c1 times y1, c2 times y2, and this is 0, so it'll equal 0. Okay, so we have this. So we're almost done now. I'm out of space here, so let me erase a few things and we'll keep going. Okay, so here's the proof continued. So here's where we left off up here. And recall our y equals C1y1 plus C2y2. This is what we're trying to show is a solution of the differential equation here. So let's look at what y prime would equal here. So let's compute y prime right here. Okay, so the first thing to note here is that y prime then will be C1y1 plus C2y2 prime, and the derivative is a linear function. That means you can take derivative of each piece separately. The c's are constants here. There's going to be C1y1 prime plus C2y2 prime. Okay, and let's look at now y double prime. So let me do y double prime here. So doing that we get then. Okay, so looking at y double prime now, and it's going to be the derivative of this guy, again using the linear property, is going to be then C1 y1 double prime plus C2 y2 double prime. And now we can substitute this guy here. So in place of this guy we can write y double prime, and in place of this we can write y prime, and in place of this guy here we can write y. So let's make those substitutions. So making those substitutions we get then, okay, so making the substitutions then, so again that's y double prime, that's y prime, that's y. We'll have y double prime plus p of x y prime plus q of x y equals 0. So hence we have shown that y equals c1 y1 plus c2 y2 is a solution of star. So star was our original differential equation. So we're done with the proof. So you can put like a little box at the end. That means the proof is over. Okay, so we're done with the proposition 1. Okay, so let's move on. I'm going to erase some things here and we'll move on. Okay, so next thing, a set of functions, so say f1x, f2x through fnx, so say you have n functions here of x, is said to be linearly dependent on some interval I if there exists coefficients c1 through cn not all 0, such that c1 f1x plus c2 f2x plus cn fnx equals 0 for all x and I. Okay, and the functions are linearly independent, Li, if they are not linearly dependent. So let's take a look at a simple example, and then we'll look at some more examples. So first example. Okay, so here's an example. So suppose we have these three functions, f1 equals x plus 1, f2 equals x, and f3 equals 2x plus 1, and say we want to determine whether these are linearly independent or linearly dependent. So here's an intuitive way of thinking of linearly dependent. So the functions would be linearly dependent if you can make one of the functions from the other ones. So could we take two of these functions and make another function from these? So could we use, like, for example, f2, so f1 and f2 to make f3, or f1 and f3 to make f2? Well, just going to show you here. You should notice here if I add f1 with f2, so it'd be 2x plus 1. So pretty much f1 plus f2 would equal f3. So let's note that here. Okay, so notice here x plus 1 plus x equals 2x plus 1. So x plus 1 is my f1, the x is my f2, and the 2x plus 1 is my f3. So we have then 1 times f1 plus 1 times f2 equals f3. So pretty much we can make the f3 function from the f1 and f2. So I claim that implies linearly dependent. You might say, hold on a second, but the definition here has it equal to 0. That's true. But once you have it as a combination like we have here, so f3 made from f1 and f2, I can just move to f3 over here. So doing that, we get then, so I've moved the f3 across here, then I'll have then 1 times f1 plus 1 times f2 minus 1 times f3 equals 0. So you can think of the c1 then up here, if we're going to match it up with this guy up here. The c1 would be 1 here, the c2 would be 1, and the c3 would be minus 1. So you can see what this is really saying up here if this condition is true, it's really saying that one of the functions can be made from the other functions. So here we've shown that f3 can be made from f1 and f2. This in general is saying that one of the functions in here can be made from the other ones. So if that happens, then it's linearly dependent. And if it doesn't happen, then it's linearly independent. Okay, so let me just write that here. Okay, so informally, the linear dependent definition, what that means is one of the functions can be made from the other functions. I guess it's kind of hard to see it's saying that here, but essentially that's what it's saying in the definition. So here the f3 can be made from the f1 and f2. So in general, a set of functions is linearly dependent if one of the functions can be made from the other functions. Okay, so this video is kind of long right now, so I'm going to leave it here and we'll continue with part 2 in the next video. Okay, so let's leave it there.